Good morning. So in previous video, I have explained about the third module called telecommunication traffic. So we discussed about the introduction, unit of traffic, congestion, traffic measurement. So today we'll go for a mathematical model. So we'll discuss the mathematical model for telecommunication traffic. So which is mainly consists two different types of systems. One is a lost call system and a queuing system. So in previous video, already I have explained about what is lost call system and what is queuing system. So we'll continue these things. So before that, so we'll solve some one more example based on telecommunication traffic. So three examples already we have discussed. So the fourth one, let us start. So this is the fourth example. During the busy hour, 1200 calls were offered to a group of trunks and 6 calls were lost. The average call duration was 3 minutes. So find the traffic offered, traffic carried, traffic lost, and grade of service. The last one, the total duration of the periods of congestion. So let us go through the question. During the busy hour, so busy hour, so always we're supposed to take the capital T as 60 minutes because it's a busy hour. We are assuming that it is a busy hour which consists 60 minutes. So 1200 calls were offered to a system. So out of 1200, so 6 calls were lost. So it means only 1194. So 1194 calls were carried. So we're supposed to identify the traffic with respect to all these three things. One is traffic offered with respect to the calls offered, traffic carried with respect to the calls carried, traffic lost with respect to the calls lost, and then grade of service and fifth one, right? So we'll start with the first one, the traffic offered. So we know that A is equals to CH by T. So here C is going to vary. What is C? We're supposed to consider traffic offered in the sense it is related to calls offered. So 1200 calls were offered to a system. It means C is 1200. So 1200 into 3 divided by 60. That gives a 60 Erlang of traffic is offered to a system. So out of that, so we know that 6 calls were lost. It means 1194 calls were carried within a system. So it means traffic carried. So here C is going to change. That is 1194 into 3 divided by 60. It means 59.7 Erlang is a traffic carried because 6 calls were lost. So then amount of traffic lost we're supposed to identify. The third one, A is equals to CH by T. So here C is going to vary. So this is with respect to the calls lost. How many number of calls were lost? So 6 calls were lost. So 6 into 3 divided by 60. So 0.3 Erlang of traffic is lost, right? So the fourth one, grade of service. So we already defined that grade of service is nothing but the ratio of traffic lost to the traffic offered. So what is the traffic lost here? 0.3 Erlang. And what is the traffic offered? 60 Erlang. So 0.3 divided by 60, 0.005. So it doesn't have any unit. So the grade of service of this system is 0.005, right? So we know the meaning of grade of service. The lesser the grade of service, better the system, right? So if it is 0, it becomes an ideal system, right? So we need to avoid the increase in the grade of service. If it increases, the system becomes very worst because the number of calls where lost is increases, then grade of service increases. So that's why try to avoid the lost calls. So the fifth one is the total duration of period of congestion. So total duration of period of congestion is supposed to identify. So here 0.005 is a grade of service multiplied with the seconds, right? 3600. So in 1 hour 3600 seconds are there. So 0.005 into 3600. So we'll get 18 seconds. So this is the congestion period. 18 seconds, right, is the congestion period because the call lost are very less, that is 6. If lost calls increases, so this congestion period is also increases. So try to avoid the congestion, right? Because it's a situation, right? So where it becomes complicated for a telecommunication system. So two things we need to keep that in mind. So for a better system, we need to reduce the grade of service and we need to reduce the total congestion period. So this is the fourth example which is from the question paper. So it's an important one, right? Try to practice it, you'll come to know. So next we'll go for a mathematical model, very important part of this telecommunication traffic. So in order to get the analytical solutions, so it is necessary to design a mathematical model for a teletraffic problems. So telecommunication problems are there, so we need to provide some mathematical equations so that we can get the analytical solutions. So before going to the mathematical models, we're supposed to go for following assumptions. So there are mainly three assumptions. One is pure chance traffic, statistical equilibrium, and full availability. Right. So these are three assumptions we are going to make before going to the mathematical models. So we'll discuss one by one. So first we'll start with the pure chance traffic. So let us define what is pure chance traffic. The assumption of pure chance traffic means that the call arrivals and call terminations are independent random events. So number of calls arrives to a system and the calls were terminated at the system. Both are independent events, independent random events. There is no dependency between these two, call arrivals and call terminations, right? If the call arrivals are independent random events, their occurrence is not affected by previous calls. So whatever the number of calls which are arrives to a system, right, they are independent random events. So that's why they are not affecting the previous calls. If they are dependent, they are going to affect its previous calls. So if there is a dependency, directly it is going to affect the traffic. So that's why, so these are independent random events. So we are assuming that, right? So these are independent random events. If they are dependent, so it is not possible to derive the mathematical model. So that's why sometimes we are calling them as memoryless traffic, right? Memoryless means there is no dependency. So this is one assumption we are going to consider before defining the mathematical model for a telecommunication traffic. So next we'll go for the equation. So based on this assumption, that is random call arrivals and terminations, so we are going to get the probability, right? So the probability of call arrivals is a Poisson distribution, right? Equation expressed in Poisson distribution. So what is that? The probability of call arrivals to a system, that is denoted by P of X. So P of X is the probability of call arrivals to a system is given by mu raised to x by x factorial e raised to minus mu, right? So P of x is nothing but mu raised to x by x factorial e raised to minus mu. It's a Poisson distribution with respect to the probability of call arrivals to a system. So where x, so this x is nothing but the number of call arrivals in a given time of capital T, and mu is the mean number of call arrivals in a system. So there is a difference between the number of calls arrivals to a system and mean number of call arrivals to a system, right? Because whatever the calls which are arrives to a system, that is denoted by x, right, during the busy hour, and we're supposed to take the average of all these calls with respect to the busy hour, right? So that gives mu. So there is a difference between x and mu, both are not same. So the probability of call arrivals to a system is nothing but mu raised to x by x factorial e raised to minus mu. It's a Poisson's distribution. Next, we're supposed to identify the probability of the time intervals between the call arrivals and the call terminates, right? Because both are independent random events, and how much time it will take. So probability of that time interval we're supposed to identify. so which is given by the probability of time interval t greater than or equals to small t. We know the difference between capital T and small t. Small t is nothing but h by capital T, right? Holding time divided by the time interval. So capital T and small t are different. So probability of time interval between the call arrivals and the call termination. So P of t greater than or equals to t is an exponential distribution, which is nothing but e raised to minus t divided by t bar, right? So where t bar is nothing but a mean time. It's a mean time, average time, right? So we can also express this t bar as h. So this equation can also be rewritten as p of t is greater than or equals to t is equals to e raised to minus t by h. So only we have replaced this one because it's a mean time. Mean time is nothing but a holding time h, right? So we can also write this equation by this one. Both are same, right? Next one, statistical equilibrium. The previous one is pure chance traffic. So now we have a second assumption, that is statistical equilibrium. So the assumption of statistical equilibrium means that the generation of traffic is a stationary random process. It is a stationary random process. That is, the probability do not change during the period being considered, right? So whatever the time we have considered, whatever the period t we have considered, so during that time the probability is not going to change. So average probability we supposed to consider, right? So we are assuming that it's a stationary random process. Actually it is not stationary, it is going to vary, right, at every minute. So there are probability is going to vary. So if so, it cannot be identified, right? So if this is a variable, cannot be identified. So that's why we'll assume that it's a stationary random process. It means it is average, right? So throughout the period what we have considered, the probability is equal, right? Equal distribution is there. This is an assumption. Actually, probability is not equally distributed throughout the time t. It is going to vary, right? So consequently, the mean number of calls in progress remains constant, right? So whatever the mean number of calls are in progress during that considered period, so all are constant. Actually, they are not constant. They are going to vary. But this is an assumption before going to the mathematical model. So we're supposed to consider that statistical equilibrium, right? The probability is stationary random process. It is not going to vary, right? So let us solve some examples based on these two equations regarding the pure chance traffic, right? So the first one, on average, one call arrives every 5 seconds during a period of 10 seconds. What is the probability that no call arrives, one call arrives, two call arrives, and more than two call arrive to a system? Right, so this is the question which is important one and asked in one of the question paper, right? So you're supposed to analyze the question before in solving any type of problems. What are the given terms? On average, one call arrives every 5 seconds during the period of 10 seconds, right? So the total period is given 10 seconds. So call arrives every 5 seconds. Then within this 10 seconds, how many number of calls arrives? Two calls, right? So two call arrives within this 10 seconds, right? So it means the probability is, it may be a 0, it may be a 1, or it may be a 2, or it may be more than 2, right? Not 3, 4, 5. Total probability is supposed to consider. So 5 seconds call arrives every 5 seconds means we have a mu is equals to 2, right? Average number of call arrives. So every 5 seconds one call, so 10 seconds 2 calls. The value of mu, average number of calls, is 2, right? In this example. So no call arrives means probability 0. So P of 0, we know the equation, the Poisson equation. P of x is equals to mu raised to x by x factorial e raised to minus mu, right? So the first thing, the probability of no call arrives. No call arrives to a system in the sense 0 probability. So P of 0, 2 raised to 0. Substitute the value of x as a 0. 2, the mu value is 2. So 2 raised to 0 by 0 factorial e raised to minus 2. So it gives 0.135. It doesn't have any units because it's a probability, right? 0.135 is a probability of no call arrives to that system. So now the second one, probability of one call arrives to a system. So x value is 1. So 2 raised to 1 by 1 factorial e raised to minus 2 is equals to 0.270. So that gives the probability of one call arrives to a system, right? So the next one, the probability of two call arrives to a system, the x value must be 2, right? So 2 raised to 2 by 2 factorial e raised to minus 2. So the value is 0.270, right? If you substitute all these things, you'll get 0.270. And the probability of more than 2 calls arrivals, it means the total probability is 1, and the probability of no call arrives, 1 call arrives, and 2 call arrives. So we're supposed to subtract all these three from 1. We'll get the probability of more than 2 call arrives to a system, right? So 1 minus 0.135 minus 0.270 minus 0.270. So what we'll get? We'll get 0.325. So this is the probability of more than 2 call arrives to a system, right? See, x is the number of call arrives to a system and mu is the mean number of calls, right? Every 5 seconds one call arrives, the total duration is 10 seconds, so 2 calls arrives to a system is possible. So mu value is 2 in this example. That's why, and we suppose to substitute all the x values here, we'll get the respective probabilities, right? So we'll go for the next one. In a telephone system, the average call duration is 2 minutes. A call has already lasted 4 minutes. What is the probability that the first one, the call will last at least another 4 minutes? The call will the call will end within the next 4 minutes. Right? Already it lasted 4 minutes, but the average call duration is 2 minutes. Average call duration, it means H. The H value is 2, right? It is already lasted 4 minutes. The T value is small t. Small t value is 4, right? So we're supposed to identify the first one. The probability of the time interval t greater than or equals to small t is equals to e raised to minus t by h. Already we have discussed about this equation. So here t value is 4. It is already lasted 4 minutes. And h value is 2. The average time call duration. So 4 by 2 it gives 2. So e raised to minus 2, that is nothing but 0.135. So this is the probability that the call will last at least another 4 minutes. This is the probability, right? And the next one, the call will end within the next 4 minutes, right? It means the probability of time interval t less than or equals to small t. It's nothing but 1 minus of this one. Total probability is 1, and this is the first probability. So 1 minus this one will get the probability of time interval less than or equals to t, right? So that is 0.865. The second one is the call will end within the next 4 minutes. The probability is 0.865. The probability of the call will end within the next 4 minutes. It is 0.865. So this is how to solve the probability examples, right? So in the third video, we'll discuss about the queuing system and the lost call system. So designed by the scientist called Erlang. So that's why we are calling them as Erlang's first distribution equation and second Erlang distribution, or Erlang's second distribution equation, right? Simply, we are calling them as first Erlang distribution, second Erlang distribution. So two mathematical models are there. So we'll discuss in the third video, right? So whatever the things we discussed previously, based on all these things, we are going to derive two equations for first Erlang distribution and second Erlang distribution. So first Erlang distribution is with respect to the lost call systems. Second Erlang distribution is with respect to the queuing systems. So designed by Erlang. So that's why the name is given as first Erlang and second Erlang distribution. Right? So we'll discuss these things in the third video. Thank you.